So as we have just discussed that introduction slides in this chapter number 12, we have discussed about the instruction set architecture. In short, it is ISA, and we know that for any microprocessor, for any kinds of microprocessor, if you want to know about the microprocessor, their architecture, and if you want to write the assembly language code for them, you need to know about instruction set architecture, because this instruction set architecture provides you an idea about the internal structure and organization of any microprocessor. It tells you that how you are going to write the code, what will be the type of the instruction, how you are going to write those instructions, what will be the interpretation process or assembly process, and how the microprocessor connected with other register, how many register do you have. This kind of all information you can get from this instruction set architecture, in short ISA. Previously we have done this one into chapter number 3. We have discussed thoroughly about this ISA of Pentium processor. Here we are going to discuss about RISC types of processor, that means MIPS processor. Okay, so one example of that previous CISC processor, we know that all of them, like 32-bit processor, let's say for example Celeron Pentium processor or Xeon. So these are all 32-bit processor, we know that, and it is all of them following IA32 architecture. So what is IA32 architecture? Which is Intel architecture. 32 means it's all of them are 32 bits. That's why Intel architecture of 32 bits. And we know that although they are all 32 bits processor, but some of them are not similar, have similar performance with compared to the others. So say for example the Celeron processor. Celeron processor, of course, is a cheaper version of the processor where you can use a low-end PC or laptop or any other devices, whereas the Pentium 4 and the Xeon processor is actually using in high performance, very good configuration workstation, laptop or PC. Okay, so although, why I'm telling you, because although they are following the similar architecture, but their performance is not same depending on the manufacturer and depending on the model name. Okay, so uh, let's start with a discussion about the design principle of the RISC processor. We know that RISC, whenever you try to understand any microprocessor for your assembly language code, you need to know their design, internal design, how they works, what are the issues they have, what are the characteristics and functionality they have. So these are design principles. So in this chapter, they have several. I have mentioned here for 6 types. Right. The first type is the simple operation. We know that our RISC types of processor are not a complex instruction. They are very simple one compared to the complex instruction in the CISC microprocessor. Okay, so if you think about this picture, which is from the book, figure 2.1, 12.1, where you can see that one is the left side is the CISC implementation and the right side is RISC implementation. What is the difference is whenever you write any code, right, whatever you have instruction into ISA level, in between that one and hardware, direct hardware, there is a microprogram controller for CISC processor, because we know that we just written one complex instruction, and that complex instruction is combination of several other low-level instruction. Okay, so that's why to do all this other instruction within that one complex instruction, the CISC processor needs a microprogram controller. I mean microprogram controller. This program controller using to transfer all the complex information into the hardware level, so the hardware can identify and then can follow the instruction. Whereas into the RISC implementation or the RISC processor, whatever you write in the code, right, by using the ISA architecture, it is directly can be understandable whenever you convert into the machine language, directly understandable by the hardware. You don't need any other intermediate thing, unlike the CISC processor, because one instruction in this CISC RISC processor just need one clock cycle, because it's very simple one, although it's require more clock cycle for several others, but single instruction required one clock cycle, whereas in the otherwise in the CISC processor, single instructions require multiple clock cycle because it is a very complex one, and it is also a combination of other low-level instruction, and microprogram controller needs to handle those other complex ones. So that's why our RISC processor is quite simple to operate. And the second one is the register to register operation. If you think about the CISC processor using memory to memory operation, and that's because they need to, store or need to avoid using more memory because it was invented long ago, like 1978 or 1974. At that time, we have very less amount of memory. That's why the architecture of the CISC, they design in that way that they don't need that much memory. But whereas in the register to register processor, here in RISC processor, because they're using register to register, it is faster. Of course, it is more efficient than sometimes it is not all of the time. Sometimes it is more efficient than the CISC processor also. But there is only one case where you need to, that means RISC processor need to do their operation in main memory, and that one is the load and store. I'm sorry, in that situation is only the load and store operation. So that means only whenever you're going to do the load or store operation in the RISC processor, only then you're going to use the main memory. Other than that, every time you're going to use register to register. Fine, so that's why it says register to register operations. Third one, it says a simple addressing mode. Okay, if you can remember in the CISC processor, whenever we have discussed about CISC processor, there are 4 addressing modes. Although there are so many other division, which is chapter number 6, we didn't discuss it, but we know that initially there are 4 types of addressing mode, and they are a little bit complex whenever you are trying to understand about direct and indirect addressing mode. But here in RISC processor, they have just only one, which is the register based addressing mode, which is really simple to implement. All right, so that's why it's called simple addressing mode. We will see some of the simple addressing mode in the later slides. So the fourth one is large number of register. Of course, the RISC processor require comparatively more register, because this RISC processor, all the operations, most of the operations operate in the register to register, right? That's why we need more number of register compared to the CISC processor, because CISC processor is using most of the time memory to memory. That's why they require less, but RISC require more, and they have more register. So the fifth one is fixed length. Of course, it's the fixed length because whenever you write any code into the RISC or the RISC or MIPS processor, when they convert it into the machine language, the length of the machine language code is always same, whatever you write in the RISC microprocessor. On the other hand, if you write anything from the CISC processor, when you convert it from the CISC to machine language, the length of the machine language for CISC instruction, they are not always same size, the length. It varies. All right, so that's why it's very simple one. And the last one is the last design principle we have discussed earlier, that it is there's RISC, most of the RISC, not all of them, using Harvard architecture. So what is Harvard architecture is, in this architecture, the processor using separate path for data and instruction. That means you have separate path for the data and separate path for the instruction. This is called Harvard architecture. Although there are other features here, but we have not. I have not included into here. So please remember these six basic design principle. One is the simple operation, register, simple address, large number of register, and fixed length of the instruction, and of course it is implemented Harvard architecture. All right, so let's go to the MIPS architecture. By the way, in this chapter or in this book, they have decided to use R2000 as a MIPS processor. What is the reason to using this R2000 is this R2000 MIPS processor, it's very close to the original architecture of the RISC processor. Okay, very close to the original architecture of the MIPS processor. That's why they have chosen this R2000. Fine. So let's talk about the register, which is very important for any microprocessor. By the way, we will discuss very little about the register, and then we are going to discuss about the addressing mode, although we have just only one types of addressing mode, and then the how they're using the memory. Okay, these three things we are going to discuss. That will the end of this MIPS architecture. So the register, if you can remember, in the CISC processor, in Intel Pentium processor, there are several types. Let's say 4 types of processor: data register, index point register, then the control register, the segment register, like flag register. So those are the register into the Pentium processor. But here we have generally 3 types. One is the general purpose register, of course, a program counter. We know that it's a very simple one, and 2 special purpose register. Okay, so please remember these 3 types. All right. Of course, general purpose register, very similar as the CISC processor. We also have general purpose register like data register. So we have general purpose register. Okay. And by the way, there are 32 general purpose register, one 32-bit program counter, in short PC, and 2 special purpose register. Okay, and all of them are 32-bit wide. Let us see the picture in 12.2, which can show you the picture of these 3 types of register. Let me show you. It is page number here. This one. Look, as I said, that we have 3 different types of register, and all of them are 32 bits. By the way, all of them are 32 bits: 0 to 31, 0 to 31, 0 to 31. So the first one is a general purpose register. So general purpose register has they have 32 different register, which are general purpose register. Each of them has its own responsibility, and they're using for different purpose. 0 to 31, that means we have 32 general purpose register. We have another one is the program counter, PC, also the same 32-bit. We have 2 different special purpose register, HI and LO, which they have used for multiplying and dividing purpose, and also the other purpose. So just remember, we have these 3 types: general purpose, program counter, and 2 special register, and all of them are 32-bit long. 32-bit long, all of them. Fine. Okay, so let's see what are the responsibility. Very specific general responsibility. Okay, if you compare with the Pentium processor register, they have their own name, right? Depending on the responsibility, they have own name like EAX, CBX, CX, TX, AL, AH, BL, BH, something like that. But here in MIPS processor, they identify by its name. I mean by its number. We know that we have 32, so the name of the first register is actually 0. The name of the second register, general purpose register, is 1, like that. It's actually going to 0 to 31. So the name of the register, right, they can call there by name, like this, with a $sign. I hope you remember in chapter number 1, we have discussed some of the instruction which is related to the MIPS processor, where we have used the $sign to identify that this is a register, like the same way. Okay, so they can identify by this $sign and the number of that register, 0 to 31. Fine. And one interesting thing is the first one, 0, this register, and the last one, 31. These 2 register is reserved for a special purpose. They have reserved. Especially the most interesting thing is this one, the 0 register, is using for if you need any value from any register where the value is 0. Okay, this 0 register will give you that value 0. Quite interesting, right? That means if you need any value 0 for any purpose, this register will give you zero register, zero number register will give you that value, so that you can have a value of 0 from this register. Okay, so there are several. There is a list. Let me show you. There is a list here. These, as I said, they are conventional use. Okay, so these are the architecture that, yes, you can, for this register you can use this and that. By the way, good news is you don't need to memorize this one. I'm just showing you for your reference. No need. Okay, no need to memorize, because it is nothing to memorize. So just for your reference, that for 0 to 31 we have separate responsibility for each of them. All right. Okay, and they have, although there are other name also. I hope you remember that, where sometimes we have used T, if you remember, in chapter number 1. Fine, it's the same similar thing. Okay, so that is our register. We have okay, we know everything. So one last thing is, we know that about our instruction point registers. Okay, we know that this one PC. So we know which is the general purpose with the table. So now let's talk about the PC program counter. I think it's very common, super common register for all of the microprocessor, because most of the microprocessor has this program counter PC. Wherever in the previous types of microprocessor, that means the Intel microprocessor, we have another similar types of register, which is called EIP. This one, instruction pointer in Pentium processor. So instruction pointer and the PC, similar thing. Okay, instruction pointer and PC, similar types of register. So they are giving you the comparison, so that you can understand that which register's responsibility, what the type of the register, easier. And there is two other types of the register. One is the HI and LO. These are the special types. And of course, as I said, that they are using for doing multiplication and division. These two one. Low end, I think LO means low end, or H means in the high end or something. Okay. So these two special purpose register are using for multiplication and division to store the result. So these are all the register. Let's see about the addressing mode. I have told you that in this MIPS architecture we have only one register based addressing mode. Okay, but only when we know, because these are register based addressing mode, but only one issues, or only one instant they have to access the main memory, which is the load and store architecture. Okay, that means the load and store architecture only can access to the main memory properly. Fine. So just only one addressing mode, which using the register. It is register based addressing mode. Unlike the our previous Intel processor, they have used several types. They have register based, they have immediate one, and they have two types of main memory based on the main memory also. But here we have only one type, which is the register based. Although there is some little bit exception that whenever you're going to do the load and store architecture, only then it's using the main memory. Otherwise, it is always all about the register. Fine. By the way, you don't need to know anything more about the addressing mode of this MIPS processor. If you know this much, it's enough. The last topic is the memory uses. Okay, let me show you a picture. I think the picture number is 12.3. Let me show you the picture about our memories of this one. So let's say this is our memory. I mean, this is the memory of the MIPS processor. So how the MIPS processor going to allocate the memory, or going to manage the memory. Here in the main memory, there are three parts. One is the code, another one is the data, another one is for stack. Remember, these three is very important information. These three information is important. That means in the memory, we have three parts: code, data, and stack. Code, data, and stack. Okay. Look at this memory layout. We have some reserved word. Okay, we have some reserved words for their special types of execution. the rest of the part we are going to allocate or going to manipulate our memory or using our memory by these three different types: data, I mean code, data, and stack. Okay, the you can see the text segment. This is actually the data. Don't get confused. This is actually code. Although they have written text segment, but this is the code segment. So here, wherever you have some instruction or code or anything related to it, you can store it here, which is started from this location. By the way, whatever you are seeing, the number, these are the memory address, and this memory address is true for only MIPS R2000 processor. Do not think that this is everything, whatever we are discussing is universal. Nothing is universal. It's very, very specific to a very, very specific microprocessor. Okay, whatever the layout you are watching, or whatever the discussion you are seeing, or whatever the functionality we are discussing, this is all about MIPS R2000 microprocessor, which is the RISC type. Okay, don't mix it with the other microprocessor. It is very specific for this kind of microprocessor. You might thinking that why we are discussing this MIPS R2000, because as I said, this MIPS R2000, the functionality of MIPS R2000 are very close or almost similar to the basic architecture of the RISC processor. Okay, they are very similar. That's why they choose this one, MIPS R2000. Okay, so all of whatever we are watching or discussing, everything is related to MIPS R2000, and also is very similar to the basic architecture of RISC processor. Fine. So okay, so let's come back. So we know that there are three different part or types of the memory segment we have in MIPS processor. First one is the code, then is the data, and then after that it's the stack. So the text segment we are watching here, this is the code. Fine. After that, it started from this location. After that, we have data segment. We have two types of data segments, static and dynamic. So these are the data segments starting from this location. And on the top of that, we know that our stack should be in the top of the memory location generally. So our top of the stack will be top of the memory location will have the stack segment, and the other one are unallocated one. That means that you can use it for any other purpose, or you can extend your for the data or data segment or the stack segment or any other purpose or for any other application. So these are the three basic things we can allocate into our memory location: code, data, and segment. And that is the layout, approximate layout of MIPS 2000, MIPS R2000 processor. Okay, fine. By the way, as I told you again and again, this is just a layout for a very specific microprocessor. Okay, very general view. So that we have an idea that how the MIPS processor, other types of the MIPS processor actually do their own task. If the other types of MIPS processor may not be same, and also may not be entirely different, similar, but they have changed a little bit here and there. Okay, but similar types of things. That's why we are studying this MIPS processor. Okay, fine. So that is all about the memory uses of MIPS architecture.